Okay, so I went through the question, the comments in the sticky notes, and there was one that attracted my attention, and this person says that they really enjoyed the challenges, and some additional ones would be great. And so if we look back on the teaching material, okay, where is my teaching material? Bit.ly suite may instance. If we look at, for example, material day 2, there are some of the dployer examples maybe. Okay, so here there are always challenges with the answers already present. Okay. So there are additional challenges. We don't have time to do all of them, but the material is there with additional exercises in case you want more. Do I need to reduce the fonts a little bit? Yes? Is it okay? I'll try to reduce them a little bit. As you see, I read the notes. I find it's difficult when they are so big too. Where was it? Tools, global options, appearance, 24. Let's try like this. If that's too small, we can move it back to 24. Okay. And so what I want to do is to, before we start with the visualization, is to briefly show you the last part of the set of functions or manipulations we can do using dployer, and that is grouping or group by. So I start with my IPRG dataset that has 36,000 observations, and so on also. And then if I say group by, and I want to group by, for example, condition. So here is what happens. My whole data set is printed out, but what we can see here, so we still have our table with 36,000 observations and 7 variables, but now we have 4 groups. And these 4 groups represent the 4 categories, the 4 conditions that we have. Now, this grouping is done under the hood. The data hasn't changed, but this grouping we can now make use of this grouping of the data and use a summarize function. There is a British version and there is an American version, so we can use that. Fortunately, the author of dployer comes from New Zealand, so he understands that there are different ways to spell it. If it was a Brit, there would only be the S version. And so what we can now ask is to summarize, to do certain computations, but independently on these 4 groups that we have defined. So I could now say mean intensity, for example, is mean of intensity. Was it? Yeah, capital. So what do we get as output? We get a table, and that's a very important properties. All these verbs, all these actions, filter, select, mutate, group by, and summarize, they all expect a data frame or a table as input. As far as we are concerned, these are the same thing, data. data frames and tables. And they all return a table or data frame as output. That is, of course, modified, changed, and in this case, our output has 4 rows, 1 per grouping that we did, and so we have the conditions here, and then the second column that reports the mean intensity, because that's what I wanted to calculate. Mean int, which is a mean of intensity. But the mean of all the intensities of condition 1, condition 2, 3, and 4, and so on. Group by bio replicate. Another operation that we might be interested in is tally. Okay. We have bio replicate 1, 2, 3, 4, and this is the number of observation that we have per group using tally. So there are many, many different ways to use grouping by, summarize, tally, and there are many other kind of actions that can be done on grouped operations, and we won't have time to study them all today. But oh yes, sorry.
So tally is like table?
It's to count. Actually, another one I think is n to. Oh no. Count. Yeah. Count. Thank you. Oh, sorry. Count, and let's make sure that we get the same result. Yes, is there any difference, any subtle difference? Apparently not. So, tally or count? Yes?
Is there a reason why we're using mean int equal to mean intensity? Like,
so this is the name of the new column.
Oh, like mutate?
Yes, it is like mutate, and I want to calculate a new column that corresponds to the mean of the intensity for the different conditions, and I call this one mean int. It could be something else. This is something that you can make up.
Okay. We don't need to use mutate to add in
If we wanted to have the mean intensity, mean in this case wouldn't work, but if we wanted to, the example that we had is log 10. So in this case, we have a full column of intensities, and we want to calculate a new value per intensity. So if we have 36,000 intensities, we get 36,000 log 10 intensities. But in this case, we want to do a calculation, get a summary per group. So here we don't have a mutate. Here we have a first grouping by, and for each group, we take all the values of that column to calculate a new value. But the syntax is the same. New column equals calculation, but we do it column-wise per group. Here, new column calculation, it is a new one long column. Red sticker? Do you have a question? No, your neighbor? Because you have a red sticker on your laptop. Okay. Okay. So there are more exercises in the notes, but I would like now to move on to the visualization. I'm going to create a new script here, save it as script 5. A new script for the visualization, and we are going to keep on using the IPRG dataset. So we're going to see two ways to visualize data in R. The first one uses base graphics. What is called base graphics is the kind of built-in plotting capabilities that come with R. Second one we will see are capabilities that come with. Is this? I don't think this is my water. Is this anyone's water? That's fine. The second one comes from a package called Ggplot 2. And again, it has a completely different syntax, a completely different semantic, a little bit like dplyr. We will need to learn new things, but this is worth the effort. But I want to briefly show how base graphics works because it is very useful. It is very useful. You can't push it as far as with Ggplot 2, but it is very powerful. So the first thing I would like to see, for example, I would like to look at the distribution of the intensities in the IPRG data. So IPRG $intensity. So I still need to know my R syntax. This returns a vector of all intensities. And if I want to plot a histogram, I feed this into the hist function. And I need to make sure that I have enough space here. And I am going to change this pane layout. And I want here to have files and plots. Okay. So now my figures will appear on the top right. Okay. So here we go. Very kind of rough figure, but it does the job. It does it very efficiently. The hist function expects to have a vector of the numbers, of numerics. It will create the bins automatically and display the histogram. So I will not go over all possibilities to customize these figures. I'll show a few, and they can then be reused, repeated for other functions. But there would be too many ways to customize these, and they are not always all very useful. One that is maybe interesting is IPRG $intensity is the number of breaks, which I think by default is 50. And here if I specify breaks equals 100, I will get 100 breaks. Now the problem here is we can try to increase the number of breaks as much as we want. Most of our intensities are here and the very end of the scale. So it's probably more interesting to start and look at the log transformed intensities. And we have the log 2 intensities. Here it is. Our intensities in log space using hist. Instead of hist IPRG $intensity, we plot the log 2 intensities. And yeah, clearly it's maybe not the most beautiful figure, but it's very easy to produce. And somehow, I think, before creating beautiful figures, what we really want is to be able to quickly produce figures. And then once we are happy, we understand the data, we can spend as much time as we need to get it really as beautiful as we want. Okay. So, hist for histogram, there is also the box plot function to produce box plots. Again, very bare bone, but it does the job in producing box plots. I think it's very useful. Let me see if I still have it here. IPRG2, yes. So, hat IPRG. Do you remember the format of IPRG and the format of IPRG2? Something we did this morning. So IPRG is a data frame with 7 columns. One of these columns contains intensities. We have protein intensity, log2 intensity. We have condition, biological replicate, technical replicate, and we have a very long, narrow and long table with 36,000. Dimensions of IPRG2 were 3027 by 12. Here we have 3027 proteins along the rows and 12 samples along the columns. It's like a big matrix with all of our intensities. And that data set, that format, is very useful if we want to produce a box plot to look at the distributions of our 12 samples. So box plot is clever enough to know, oh, here it gets a single vector as input, so it plots box plot one distribution, but if it gets a matrix or data frame, it will produce a box plot per column. And for the sake of completeness, I'm going to show you that it's possible to obtain the similar figure with the IPRG dataset by defining the plotting like this, where we want to split the log2 intensities based on the ROP. Okay. And this is the data set. So if we use this tilde notation, R will take this long vector, but split it in 12 sub-vectors based on the value in ROM. And it produces the same figure, but with different types of inputs. So it shows that some figures are very easy to create with one format, and there are always ways to reproduce these figures when the data is in log format. In this case, it's pretty obvious, but it's not always the case. So it's important when you want to explore your data visually, it's essential to be able to manipulate it, transform it, to get it in a format where you can visualize it the way you want. Let me also maybe mention the obvious. I haven't shown yet. IPRG2, first sample IPRG2, second sample produces this scatter plot. Well, here, first sample. Second sample, xlab equals I'm going to call it sample 1, ylab equals sample. Otherwise, I have this weird notation, square bracket operator 1 and 2. So I can have that piece. Again, pretty rough figure, but very, very useful to get an idea of your samples. Last example of base graphics, pairs, IPRG2, which generalize the scatter plotting and produce a 12 by 12 matrix of scatter plots for all the columns in that data frame. The computer seems to struggle a little bit. Has anyone tried on their computer? Does it also take that much time? Oh, here we go. So, of course, the more samples we have, the more difficult it becomes to visualize. So maybe I'm going to say 1, 2, 4. So subset IPRG2, keep the 4 first data sets to use pairs. And here we go. So sample 1, 2, 3, 4. This is scatter plot for 1, 2, 1, 3, 1, 4. 2, 3, 4, and 4. and we repeat the plots in the upper right and lower left diagonal. If you look at the documentation of pairs, you'll see that these different mirror images of our matrix can be modified to represent different, to produce different plots. So this was base plotting, or base graphics, that I have to say I like very much. Maybe that's because I started to use R a long time ago, and maybe Ggplot 2 was not out there, was not as well known. So I found base plotting base graphics very useful, but clearly when you need to have more sophisticated visualizations with many covariates that you want to visualize, it will not beat Ggplot 2. So Ggplot 2 is an extra package that we need to install and load. So to load a package, we use the library function, like we did this morning for dplyr or tidyverse. And it doesn't complain. That means that Ggplot 2 was installed and was loaded successfully. If you get an error complaining that Ggplot 2 is not installed, you would say install the packages Ggplot 2. So could you put up your blue sticky notes once you have Ggplot, once it's loaded, and call us or use a red sticky note if it fails to load. Okay, so what are the big differences between base graphics and Ggplot? By the way, GG stands for Grammar of Graphics. So the idea is to define a grammar of visualization. With, let me come back to this figure here. With base graphics, it's like a painter model, a canvas model. I literally start with a white canvas, and then I add points, I add ink. I plot each element one by one. So for example, here I could say points, 22, 24, column equals red, CX for character expansion equals 3, PCH equals 19, because I want kind of a full, a solid red dot. And you see, I add something on top of my figure. And if my red dot is not exactly where I want it to be, what I need to do is that I need to start from scratch, redraw my figure, and change, for example, okay, I want it here, and I don't want it to be red, I want it to be steel blue. So it's not really producing a visualization, it's actually adding the elements of a figure one by one. And by the way, what I can do at the end, so this is my R project, and my R project so far contains 5 script files. So what I can do is at the end, store this directory, this R project directory, create an archive, and put it on the Google Drive. So you can download this zip directory, unzip it, go in RStudent, say open project, and reopen it. And so you have all the notes that I took here interactively. So that's how base graphic works. Something else that is not really great for base graphics is, the kind of default color choices are dubious, to say the least. And it doesn't have a kind of coherent interface. Like we saw, box plot works if it gets a vector, it works if it gets a matrix, it works if it gets a list. But it produces then different plots, which on one hand side is very useful because it just does something and very often it matches what I want. But this lack of coherence means that it's a lot of new information that I essentially need to learn by heart. Ggplot 2, on the contrary, works with data frames. That is the only thing it knows. The input to Ggplot must be a data frame. Typically a tidy data frame, as we have seen this morning. And then what we are going to do, we are going to build elements that we are going to combine and then ask Ggplot to represent these elements based on the grammar of graphics that it implements. The grammar of graphics, so the author of Ggplot 2 is Hadley Wickham. Hadley Wickham is not the person that invented the grammar of graphics. I think that's somebody called Wilkinson, is that correct? Can somebody correct me? Okay, I'll double check. And then Hadley Wickham implemented this kind of theory of grammar of graphics into an R package called Ggplot and Ggplot 2. So let's build, or let's look at these different components. So the first one is, we need to say Ggplot. Is it Ggplot? Yes. So the Ggplot function is kind of the first main function to build this graphical object. And we need to say that the data that we want to plot is our IPRG. It's a data frame, it's what we want to do. And if we execute Ggplot with data, this is what we get. Nothing. Oh wow, kind of a gray, because the default background for Ggplot is gray, but we don't get any axes because we haven't told what to plot. We don't get box plots, scatter plots, because we haven't told what data. We have provided a data frame, but we haven't explained exactly what data to plot and how to plot it. So we get this first object. So what we also need to specify is the aesthetics. So what do we want to map in this data set to the axes? So let's start with saying, well, on my x-axis, I want to plot my runs. And on my y-axis, I want to plot my log2 intensity. Okay. So let's run this, and we get a little bit more. We get the gray background, the default Ggplot2 background. We get an x-axis that is labeled run, because that's what we asked. And the x-axis ticks with all the runs that we currently can't read. Of course, we can fine-tune this. And then we have a y-axis that contains log2 intensity data mapped through this line here, and then the kind of ticks matching the range of log2 intensities that we have. And so we need a last piece of information to actually produce the visualization, and that's the kind of, what kind of visualization do we want to, what kind of graphical representation do we want to produce that data? And so these graphical representation all start with Jian something, and here we're going to use Jian Box Plot. So we have a data set. We map the parts of the data to X and Y labels, and now we say represent these data on this graph along these axes using a box plot. And this is what is produced. Very similar to the box plot we had with box plot. Most people would say that this one looks better, and I think we can agree with it. But otherwise, it's essentially the same type of visualization. Okay. One really interesting thing that I like very much with Ggplot 2 is that we can store these objects into new variables. So for example here, if I execute this, let me close all my figures here, yes. Okay. Here, remove all my figures. So if I execute Ggplot 2 with this data and this mapping into a variable p, I run it, nothing happens here, but I have a new variable p that was created. It appeared here. And now I can reuse this variable to say p plus Jian Box Plot. And now it will reuse the mapping and the aesthetics that I have here, plus the Jian Box Plot. And so this plus here is a special thing of Ggplot 2. That's how we combine these different elements of the visualization with a plus. And then if we wanted, and that's something we'll see later, another Jian, and not box plot, well, let's do it now. For example, Jian violin. I can reuse P, but say P plus Jian violin, and then I get this violin plot that also illustrates the distribution of these values. Okay. So I have a little challenge for you. Let me. So these are the log 2 intensities. Could you produce a similar plot, box plots for all the runs, but not with the log 2 intensities, but the log 10 intensities? There would be multiple ways of doing it. Oh, yeah, sorry. Oh, sorry. Here?
Yeah.
Yes, so that it's easy for you to read if I keep it on one line. And when I write my code, I would also keep it like that. I found it much easier to read statics, x, y-axis, rather than having on one line. And in general, when you write code, avoid long lines. It is very difficult to read code and reason on code when you have huge lines. Generally, kind of 70 or 80 characters is the maximum width for code lines. Okay. So, could you produce this box plot using Ggplot 2, not with the log 2 intensities, but the log 10 intensities? So there are multiple ways of doing it. You could use dplyr and a mutate to create a log 10, a new column, log 10, and then use this new data set to plot it. And actually, you could probably use piping, IPRG pipe into mutate, pipe into Ggplot 2, if you want. Very elegant. The piping works with Ggplot 2. What you could also do is calculate these log 10 intensities on the fly by changing here log 2 intensity by log 10 parentheses intensities. And maybe there are more ways. Okay? So could you take your blue sticky notes down unless you have already done the exercise and put them back up once you have finished? And you want to?
No, I was just going to say that within Ggplot you can use pipe for the data equal to within pipe.
Yes. So let's do that. IPRG. So what do I want to do with this IPRG data? I want to mutate mutate and call log 10 int equals log 10 intensity. And I'm running it, and I don't see much here at the bottom. but I don't see an error. So that's a good sign. And now I'm going to pipe this into Ggplot2. Now, the first argument in data here is supposed to be a data frame or table. That's the case. So I can immediately pass on x equals run, y equals log 10 int. Let's see. Oh, sorry, and I forgot. What is it called? Log 10 int. Okay. So what do we see? We see a plot, kind of the gray background. So we see two axes. The run on the x-axis, log 10 count, 5, 6, 7, and so on. Sorry, log 10 int on my y-axis, exactly as I asked. And then I pipe this into, oh, actually, do I pipe? No, I think I must say Jian Box Plot. And here we go. So until here, until line 29, we use the dplyr piping. Up to here in Ggplot2, when we switch to the Ggplot plus syntax. Ggplot has been around for quite a while, and I don't know why plus was chosen. And actually, it's not really a plus. You know, 2 plus 3 is the same as 3 plus 2. But actually, in Ggplot2, the order of the geoms will matter, as we will see later. But anyway, that's the way it is. So we pipe, and then we pipe into Ggplot2.
Well, okay, so I'll ask you a little question on this. How do you plan to do this?
Yes.
But I have a second question as well.
Okay, let's look first at your first question, and I'm going to, actually, I'm going to copy this and store this into a new variable. Okay. A little bit like we did here at the top, where I created my P that contains my data and my mapping. And then I use P plus box plot file plot. And so when we use dplyr and all the piping, we can, let me call it P2. So now everything is executed through the pipe to Ggplot2, and then it's stored into P2. And so I write my piping, and that's would also work without the Ggplot2. Generally with my piping, I write my pipe, I look at it in my console, and then when I'm happy with it, I move back to the front and create a new variable. And you had another question?
Yeah, so mutate doesn't actually change the data frame, correct? Unless you use it to overwrite the data frame.
It does change data frame. It creates a new column.
But only within that.
On the fly.
Right, like you do IPRD type mutate, then you execute that.
Log 10 I equals log 10 intensity.
If you do the dimensions on IPRD, it should still be set variables, right?
Oh yes. So let's do okay. Encol or dim. This one has 8. If I say IPRG dim, IPRG hasn't changed. Still has my 7. Yes, but here, when I run this one, I never overwrite IPRG. I create temporary variables. At every piping, there is this temporary variable that is created and exists very briefly between the piping. And then, if I don't do anything, it's printed out of my console, like if I say read.csv with my CSV file. The CSV file is parsed, is printed, and then it's lost.
So if you want to permanently add that, overwrite the same variable.
Yes. I would say IPRG, and then I overwrite IPRG. And if I don't want to override it, I could call it IPRG2 or anything. Yes. But, and generally I think that is what is very nice with this piping syntax is that you build your pipes, you kind of mini analysis when you go. You start with IPRG and then mutate, and then maybe pipe to filtering, and then piping to select, and then maybe piping to group by, and then piping to summarize. And then sometimes, your piping can become kind of 10 lines long, 10 operations. And then if you write your 11th operation, suddenly something goes wrong, and then you go back to 10, and then you look at your output, and then, oh, okay, maybe there was a typo, and then you write your 11th. And then when you're happy with the output, you rerun it, but create a new variable, for example. That is the way. So it's kind of a mini script, if you want, but that is materialized through these piping. Everything that is done through piping could be done with the syntax that we have started with the base syntax. But this probably kind of flows more the way we think, as opposed to subsetting and then putting this subset into a new, creating a vector, putting that vector into subsetting, and when you have lots of subsetting, it becomes difficult to read when you are not used to it. Any questions? So it's until 5, yes. Any questions so far? Okay, so let's try to. Okay. So Ggplot data equals IPRG, A as X equals run, Y equals log2 intensity. And so here I will add another aesthetic, and I'll ask that the filling should use the condition. So mapping X and Y axis as before, but now there is a third dimension of mapping, which is the coloring, the filling of my box plots. I haven't told Ggplot2 to represent this data using a box plot, so I don't see the coloring yet. Geom box plot. And now it will automatically look into my data set, figure out that I have 4 conditions, pick out the default colors for categorical data, which are these ones, which are better choice than the default, the base parameters we use, and automatically apply condition 1, 2, 3, 4. Note that I did not know that my 4 first examples were condition 1, the next one were condition 2, 3, or 4. Ggplot does this for me. If I had to define the colors myself, I would need to check, do I really have my first samples, well actually, in my very long data frame, I would need to, to really count what intensities correspond to what conditions, I would need to do all that work manually. In this case, Ggplot will do it automatically because I map the coloring based on the condition variable. Let me save this as a P2, for example, and illustrate a couple of additional customization that we can do here. And there is so much, so many customizations that can be done, and I certainly don't know all of them. Once I'm happy with the plot, and if it's not exactly how I want, I go and look up the documentation, ggplot2.org, and go through the documentation until I find the way to change whatever I'm interested in. So there is labs where I can change my title, my Ggplot2 figure, here it is. Labs can also use to set x equals x axis, y equals y axis. There are subtitles. There are many more. Again, I invite you to look at the documentation. I'm not very good at customizing my Ggplot2 figures. I think they actually look quite good to default as they come. Maybe one that is worth highlighting here is here, which is quite annoying. We can't read the sample names anymore. And that one would be theme axis.text.x element text. Angle equals 90. I find the theming sometimes a little bit convoluted, but maybe it's just because I'm not accustomed to it. There is a theme function, an element text function to define rendering or theming of text, and then, well, I want to apply this theming to the text of my x-axis, and so on. And if I like all this, but suddenly I prefer to have violent plots instead of box plots, I could create here maybe a P3 with violin, and then reproduce this with P3 that contains my violin plot. So another powerful feature of Ggplot2 is the following one. So let me create a P4, and I'm going to copy and paste this. Now P4 only contains the mapping. So we have seen the Jian Box Plot. I'll use this one again. But one that we haven't seen yet is Jian Jitter. So what jittering does is that it takes all the points for my first sample, and instead of aligning them to that tick, it will add a little bit of noise towards the left and the right, so that instead of only focusing on the distribution, let me rather show it like this because it's not very useful how it is. So P4 maps my data and so on, plus jitter, it displays now each single point for my 12 samples, but because this is these are categories, normally all my points would need to be aligned exactly here, which would not be very useful, so the jittering adds a little bit of noise to the left and to the right, so I can display all the points. And the reason I show this is that I can pile up, I can stack different geons. It takes my mapping, it plots the jittering, and then it overlays the box plot with the colors. And then maybe here I want to specify additional aesthetics, but these should only apply additional customization, but that should only apply to the jittering geom, and set an alpha channel, which is a transparency. So each individual point is not going to be fully opaque, but we'll have kind of 1/10 of opaqueness. And if I have 10 points or more that overlay, they will become opaque. Yes?
So, more to suggest this question. So, when would you use violent or versus?
Now, in this case, the distributions are pretty symmetrical, so it doesn't really matter. But if you had yes, so let me try to Ggplot data by PRG. Y equals no, maybe no. Imagine you have the following distributions. Here, actually the distribution of my points I have to outputs here. My distribution is something like this. Box plot will show, will say that my median is here, 50% of my points are here, and it will not tell us anything about this multiplier mode. Dividing the box will find like this. And so here we could immediately reveal that yes, they are the one. The median is here, most of the points are between this value and that value, but we have the cross rate around the median.
So, is it always revealed?
Certainly, if your data is like that, using box plots would be still. That would definitely already was with that. And plotting densities, histograms, also it depends a little bit what you want to show. So look, using different types of visualizations to represent the same properties of the data, like distribution, is good. And then you figure out what kind of figure is best to communicate the properties of your data, the data of interest, and then you would then put it together.
And follow-up question, so when would you use jitter? Like, why would we want to add noise to it?
So the noise is not bad noise. Noise is that, so if you look at these points here, so these are the outliers that are outside of the, this range. And so these are all the outliers for sample 1, it's bottom and top, sample 2, bottom and top. but they are all aligned here, all aligned there, which is fine. But now imagine we draw all the points, not only the outliers. For example, well, they should all be aligned on that line. But if we do that, we essentially have a continuous line from there to there, and it doesn't provide any form of information. So adding jittering does not add noise in this dimension. The values are correct, but it moves them a little bit to the left, to the right. Yes, and so you see here's an outlier. Let me rerun this, but maybe 0.5 transparency. One thing with Ggplot it's pretty slow. That is very, very slow. I think this computer is struggling a little bit. It's too hot in the room. But in general, if you have to generate 100 figures, you will see how slow Ggplot is. And then you might want to go back to base plotting, depending on what it is. So here is the outlier based on the box plot, and this is the corresponding point with jitter. The same thing here, same thing here. So you see, they are always moved a little bit so that we can see them, otherwise they would all be aligned. Anyway, so you still have your... Oh, yes. So could you try theme axis.x equals... So it's a much longer graph. That's a very good point. If I want to calculate 1 plus 1, the result is 2. Okay? I can split my line. I can calculate 1 plus 1 like this. Okay? It is still 2. What if I try to split my line like this? Let's try to run. I do not get 2. What do I get? Let me rerun this because there are too many ones. If I run these two lines, I get a first one from this and a plus 1. Plus 1 is 1. So these are two lines of code that print 1 twice. Okay. So I must be careful where I split my lines. These are two independent lines. If I do it like that, if I first execute this part, okay, R sees 1 plus, it executes these, and then it waits, because it knows that 1 plus is not a valid expression. It waits for me to keep on typing. And that's what this little plus means. It means, and what? I'm still waiting. And then I can, run that last one. Oh, and somehow I run the 2. I reran my first. So let me demonstrate this. Okay. It's waiting. So that is the plus that I typed. That is the plus for R telling me, and what? 1, enter. And that's 2. And that is the problem that you have. And a last, and that's probably the killer feature for Ggplot 2. I'm going to say fill equals condition. I'm going to keep this here. It's geom. But I'm going to add something new, a new concept, and that's the concept of faceting. Facet wrap. And my faceting means I have this figure. Let me run this. I have this big figure that displays all my distribution, all the parts of my plot on one figure. And faceting means split these data into soft figures, into facets. And how do we want to split it? By condition. And this is defined with the tilde operator that we also saw at the very beginning of the plotting. Here. It's very important in R. That's also how we define formula when modeling. Have you seen it today with, no, did Olga talk about it? Maybe you'll see it more tomorrow with Mina's lectures on statistics. So we had the big figure, and now this big figure is split into 4 subparts based on condition. Now we have kind of redundant information, the different facets and the colors. Yeah. So facet wrap or facet grid that will arrange the faceting in different ways. It's not exactly what I have in the notes. Do I need to? Oh yes, okay. Actually, maybe what I want to do here is tag replicate. So let's first run it like this. That's a better example where I have my technical replicate, but I don't want to fill. I'm not going to fill it here. Technical replicate A, B, C, but I want these to be split based on the condition. So condition ABC, condition 1, ABC, condition 2, ABC, ABC. And that becomes extremely, extremely powerful. Actually, let's try bio wrap. In these data, we only have if bioreplicate matches condition 1 and so on. But imagine that the data set was more complete. We have now the technical replicates within each facet. Here we have all the conditions, 1, 2, 3. Here we have all the biological replicates, 1, 2, 3, 4. Extremely powerful to produce complex figures with not much code by playing with the mapping and the facet. And so that is really where Ggplot shines. So saving the figures and saving the files that we had. The data sets, the temporary data sets, the temporary variables that we produce. First, saving figures. If we use our studio, we click on the little export button here. Save as image, save as PDF. Image, I imagine it will be a PNG. We can try. Here it is, PNG. I can also choose different formats. Directory, by default, it offers our intro, the working directory. We created a figures directory here. and then save. Oops. So let me look at files, figures, and here it is. I could also save as PDF. If I wanted to have a high resolution image, I would go for PDF. These are vector graphics, whereas the other images, PNG, are pixels. So if I zoom in, I will start to see the pixels, unless I have a really, really high resolution. Vector graphics, such as PDF, I store the coordinates. I have a point here, and the point will always be displayed here, even if I zoom in. So I don't have individual pixels that are stored. But they are, so this is very useful if we use our studio, but sometimes if we run an analysis on the server and we want to generate hundreds of figures, it's important to be able to generate these programmatically. And so this can be done with a function called PDF. PDF. First, let me tell you that what we see here, or the place where the figures are rendered, are called devices, graphical devices. The default graphical device is on screen here. If I plot something and I don't say where to plot it, by default I will plot it on my screen. If I use PDF, and I could also use PNG if I wanted to create a figure, write a figure to PNG, or JPEG if I wanted to write my figure into a JPEG file. Okay. So these functions will open another device that is not my screen. PDF and so on, these open files. They create new files that are ready to accept a figure. So I will want to create fig.pdf, or let's call it ggfig.pdf. So when I run this, and let me call this P5. So here I have P5, and then I execute this PDF. Nothing happens. Well, nothing happens on screen, nothing happens visibly happens, but something happens on disk. My ggfig.pdf file has been created. It's currently empty, and I currently can't open it. If I try to open it, it will say it's not a valid PDF file. Okay, it's kind of ready to be written. So now I'll say print P5, maybe only P5. I'm not sure if just saying P5 is enough. For now, I'll be on the safe side. Say print P5, execute this. And now, this figure, this ggplot figure, has been written to the PDF file. The last thing I need to do is to say dev off to close the device. As soon as I close my device, the size here increased to 12 KB. I close the device. That means that my file is now ready and finished. Can I click on it? And here it is. So if you have many figures to produce, you can write loops, iterate over data sets, and then dynamically create file names, print them, or visualize them, but to that device, and then close the device. And that's also kind of you save all your commands for your data analysis, for your plotting in a script, and the last bit produces the file, and it's a really great way to make sure that you can reproduce your figures. If you want to reproduce that figure with a new IPRG data set that has more samples, more proteins, you can regenerate your figures. I'm going to create a new script. 6, where I would like to show you a little bit how to save files. So what we have seen early this morning was read.csv, and we have also learnned about load. Okay? These are the two functions to read information from a file into R. There we go. No, it's read. I think I said read and wrote write, yeah. Okay, so my question was, if we have a read CSV, you also have a write CSV. There we go. Write CSV up. So let me create temp, and my temp would be IPRG filter condition. Okay. Condition is not 1. Condition is condition 1. Yes. Now I have this new variable that is very important to me, and I want to store it. In this case, it's easy to produce, so it's just as easy to read the data again and rerun the analysis. But sometimes some analysis will take a long time to run. So we'll want to write them to text. So I can, assuming my data, my variable is a data frame, then I can write it to a CSV file or to a spreadsheet. And so this is, I would use write.csv. Let's see, what do I have here? I'm going to create a new folder, and I'm going to call it output. And I want to write this CSV file to my output directory, temp.csv. Here's my output directory. And now it's currently empty, and when I execute that file, this data frame is going to be converted to a CSV file. And what do we do then? We can view it. Well, we could view it, and we would see that we have, oh, here it is. We have the CSV file with the first line, condition of Jew intensity 1 and so on. The second line, 1, which was the row name, the index, the name of the first protein, the intensity of the first protein, and so on. This CSV file. That we could, of course, reread with read.csv output temp if we want it. So CSV is, of course, a good format if we want to share the results with somebody that does not use R, or for supplementary information for paper, of course. But ideally, if you know that you're going to stay in R, or if it's a really big data set, or maybe it's not a data frame, tomorrow, at the end of the day, I will show you other data structures that do not fit in a data frame or matrix. Over lunch, I had a discussion with somebody, and we talked about 3-dimensional data structures or 4-dimensional data structures. These are called arrays. Arrays. Okay. And 3-dimensional arrays would, subsetting square bracket operator with 2 commas along the first, second, and third dimension. We have a 3-dimensional array. So an array would be difficult to write it to a CSV file. Maybe you would have multiple files for the third dimension, but that wouldn't be very useful. So in some cases, and tomorrow we'll see some special mass spectrometry and proteomics objects that do not fit in a matrix. And so in that case, unless we want to simplify them, CSV will not work. So what we could then do is to save temp into output temp.rda. And if I execute this, and I have to specify a file here, temp.rda. And you have to guarantee that if you send this temp RDA to somebody else that uses R, and they load it, they will have exactly the same object in R. Whatever operating system, from Windows to Mac to Linux, it will stay the same. From a US R to a European R, it will stay the same. There is no guarantee that things will stay the same if you convert it to a CSV file. For example, this is 1.23. Okay, this is 1.233 for you guys, but as a child, I would have read this as 1233. And this for you is 1233, but as a child, I would have read this 1,233. In Europe, not in the UK, they're not really Europe, and soon they won't be at all anymore, unfortunately. Let's not get started. Oh my God, I'm recorded here. Let's not get started with that. Okay, so if I write to CSV, how am I going to write it to CSV? Well, on this computer, if I have decimals, it will be written out like that. If I was using a kind of French installation, and my system settings were set to France, it would write it to CSV like this. So you would need to be careful if your collaborator had different system settings with CSV. So as long as you know that you are in R and you want to stay in R, I think save is your best bet. Okay. So it's 4 to 5, and Olga suggested that if possible I could stop a little bit early, so unless you have questions about what we have seen. So clearly the amount of new information has increased over time. There was a lot today, dplyr, Ggplot 2, very, very important packages, but a lot of new information. So, and the room is very hot, even the computer struggles, so it is perfectly normal if you feel a little bit overwhelmed. But the material is there, and it would have been much better to spend more time on more challenges, more exercises. But then I have already dropped some material, and I'm not sure if I'll have a little bit of time tomorrow to try to catch up or not. I will discuss with Mina, and she will instruct me what to do and how to do it. But so, we had to do compromises. So if you think there was a lot, you are absolutely right. But maybe you have some questions before we finish here? No? Okay. Well, if you're really unhappy with the timing, there was too much, not enough time, write sticky notes. If you think that despite all the material, it was useful, blue sticky notes or any other improvements or good things, write them down, please. Leave them on the table here. And I will look at them and maybe address some specific points tomorrow.